My name is Michael Caisse. I work with Ciere Consulting. We're a small consulting group spread across 5 different time zones. Work on really full stack software, and by that we mean very small processors with 2 or 4K of memory, and of course no OS, all the way up to thousands of cores spread across the internet doing something hopefully useful. Our group spends a lot of time doing networking or using previously Boost.Asio with different devices that we have linked in as if they fit inside that model, whether it's a CAN bus or some weird serial device or some proprietary thing for a robotic controller of some sort. We try to bring everything back into that model. And it's a model that we've found has been very useful for developing and to keep some of our sanity in. Everything should have 3 easy steps. One of our clients, if we don't actually have our very first set of screens that we provide to them with this wizard that has 3 steps, he just says, go back and start all over again. So everything's got to have 3 easy steps. Of course, for us, the 3 easy steps would be we should probably just use Rust, right? That's Nicole would say, just use Rust. That would be it. So in Rust, what would we do? We'd make a cappuccino first because we don't need all 3 steps in Rust. That's where we would begin. Then we would write about 2 lines of code, and we would then mock everybody on social media that wasn't writing this in C++ or something. Now I just want to put a side note in here. I actually tried to find the 2 lines of Rust that would do something useful in networking, and as far as I could tell, it just doesn't exist. So while this slide looked pretty good, and I tried really hard to find something, it didn't quite work. So instead, we're just going to use C++. And we don't actually need 3 steps either. So we're going to start off making cappuccinos too. It'll make us feel better. And so once we have our cappuccino, we'll write a few lines of code. It won't be 2, few. But then we're going to be very polite. And we're going to go back, and we are going to be nice to those nice Rust people and let them know that we were able to do it in some small piece of code. So here it is. This is our few lines of code to get something going. Wow. Now, if you were next door, you'd be hearing a movie. Am I the only person hearing the movie? Can we do it? We're already complaining about I/O streams. Hold on there, buddy. All right, so with I/O stream looking things, we can get a stream that is connected to something or another, a server, and we can go ahead and send some things out to the stream. We can read the stream like we'd normally read streams, and then print the output. So a few lines of code, we basically have networking. None of you are convinced yet. We'll talk about that in a moment. So networking TS. So it's based upon Asio. And Chris's work inside of Boost.Asio went in back in March of 2008. The library has been around for a very long time. It has a lot of users. The final publication of the TS was in Toronto. And so it's now published. You can go grab it, and it's not changing constantly. You can take a look at it. You can read it. And you can get an implementation. So Chris has an implementation inside of GitHub that implements pretty much most of it. And you can go ahead and start using the networking TS. What does it have? What does it include? It includes TCP. It includes UDP, including multicast. Client and server applications is kind of what it's looking towards. It's scalable to handle many concurrent connections. It's flexible with IPv4 and v6. It handles name resolution. It's got buffer management in it. It has timers in it. Now, if you're familiar with Asio, it doesn't have a lot of the things that you might have come accustomed to, dealing with asynchronous files or serial ports or things like that. This is a slimmed down version that is looking towards networking. It also doesn't include encryption, protocol implementations, all kinds of other things that you might want, it doesn't have. All right? This is a library to build upon. You're going to build things on top of this library. You can think of it as very low level. It's a very low level library. So let's start off with the stream, the thing that nobody liked. All right, so we have our stream. What are some of the problems right away when we look at this code that are going to be difficult maybe with the stream? Like what's the most obvious thing that's missing maybe? Error handling. We don't have any error handling. Okay, so there's no error handling. Anything else? Number 2 thing that's normally asked for? Well, it is synchronous, but that's what we're going to expect from our streams. So that's... We'll catch you later.
It looks like we don't have control over the timeouts.
Yeah, we don't have control over the timeouts. Number 2 thing usually asked for. The first thing usually asked about is like, where's the error handling? And the second thing is like, where do we handle things such as timeouts? All right, so let's go ahead and see if we can get those in there. So let's take a look at what we've done for timeouts. We can tell the stream, and this is very generic again, right? It's a very high-level idea, concept, that the stream functions, the things that the stream will be doing, they're going to expire after a certain period of time. All right, I just picked 5 seconds. They're going to expire after 5 seconds. At least now I don't have to worry about whatever the OS implementation has, but they're going to just be 5 seconds. Now, as far as error handling, we have to do errors the same way that we normally do stream handling with, or errors with stream handling. So we're going to check whether or not the stream returns a Boolean false. And then if it is false, then there's an error when we test it. And we can go ahead and get the error out. S.error, any idea what that might return? What would you want it to return? An error code? What kind of an error code? A what? Yeah, we've got them like built in, right? Like we would like to actually have the errors that are built into the standard now. And so that's what we're going to get. So how many people are not satisfied? That's fewer people than I would expect to be not satisfied, actually. Really? So you got... How many of you would just like want to go out and just use streams for doing your networking? How can you be both? How can you be wanting to do the streams and also not satisfied? This is a very confusing group. How many of you were not paying attention?
We just want networking in any form.
Yes, okay, so yes, networking in any form, in every form. So what is this error code? Error code entered into C++11. Error code is really a great idea. And the idea of error code is that we could talk about error categories, errors that are of a specific type that we might be interested in. And those categories are these high-level concepts. And at the same time, we can capture platform-specific errors. So we're not going to lose the platform-specific error. That will continue to bubble up. And we have something that we can be more general about and we can actually make decisions upon. So that's a great idea. That's often a problem. You write code for a very specific platform. You try to run it on another platform. And then you've got to come up with another scheme to deal with the errors on that platform because you're dealing with platform-specific errors. All right, so most of you are dissatisfied, but this actually handles the time to hello world. And time to hello world is how we make buy decisions all the time. Most people reject the original ways that we've been doing networking in ASIO immediately because they look at it and it's crazy complex. I want something easy. But as soon as I've showed you something easy, you wanted timeouts and how do we handle errors, and you're thinking about like, I want this to be asynchronous. You want the complexity. You know why? Because you're a bunch of C++ programmers. That's why. You're dissatisfied all the time. That's just kind of how we live. All right? We want something that looks easy, the syntax is beautiful, and we want like ultimate control. That's one of those places if I had like a really deep voice, ultimate control. We want it all, right? And if you spend a little bit of time thinking about things you might have to do occasionally, sometimes you just need to slap together a routine that goes out, grabs something, pulls it in, and does some work on it. And I don't know about you, but I fall into maybe some other language, scripting language of some sort, to do that. And we're getting to the place where we don't have to necessarily do that. This would satisfy potentially some of my needs. All right, so we have needs that are this simple, the time to hello world needs, but most of us, not so much. All right, I've got 3 daughters. They're all adults now, but when they were younger, they would make me coffee, and it was great. In order to live in our house at the age of 5, you have to work the cappuccino machine. Otherwise, you have to move next door. So daughter number 1 would come in, and I'd say, hey, please make me a coffee. She said, sure, Dad, and off she would go to the cappuccino machine. Hear frothing of milk, all these things. But meanwhile, I am still working. I am writing code. I'm doing things. So this time passes, and she comes back into the office. Here's your coffee, Dad. Thanks. That was an asynchronous transaction. That was awesome. All right, daughter number 3. So daughter number 3 was very enthusiastic about making coffee. But we would both get up and walk to the machine. And as she would make coffee, I would supervise, which means I wasn't allowed to touch anything. I probably shouldn't say anything either, but I'm going to make sure things are going the way they want to. Something's not ending up in my coffee that I didn't want in my coffee, things of that sort, all right? And then we would both walk back to my office, and she would deliver the coffee to me, and I would say thank you. That is a synchronous transaction, right? And we do those all day long. It just makes us sad. So when should we do synchronous I/O? What are some of the times that we might want to do synchronous I/O? On-off tasks, is that what I heard? One-off tasks, okay?
Yeah, the hello world. I need to get something and I'm done.
Yeah, need to get something and I'm done. One-off tasks, that's one. How about, yeah? Yeah, you don't have anything else useful to do. You might as well just sit there, right? Absolutely. There's no reason to add a lot of complexity in your system to add complexity in your system, right?
When you already have a background task, then you don't need it to be synchronous.
Yeah, okay, there's already a background task going. So in essence, there's some other task running. Yeah, okay, right?
You need to synchronize with some other processes.
Okay, potentially need to synchronize with some other things. All right, so often simple programs, the defaults at your system are appropriate for what you're trying to solve. Those are 2 good times. The other is fine-grained control, and sometimes it's the one that we forget. So if you need really fine-grained control of something, and you have a keen understanding of how the underlying thing works, blocking synchronized I/O is going to have a lower latency and be faster for that one thing than anything else, right? And that might be what you need the answer for. That might be. The synchronous example with my daughter is actually not a bad example. I needed some fine control over that process, right? I didn't want the coffee to end up wrong along the way. There needed to be maybe some fine tuning. All right, so synchronous example. Now we're barely fitting on a slide. Things are getting a little bigger here. So let's step through this. What does it look like? At the top, we have this I/O context, and we're going to talk more about the I/O context later. But we're going to create an I/O context. If you have used Asio before, this is very similar to an I/O service. And so we create an I/O context. We pass that off to each of the things, each of the objects that we're creating along the way, and it uses different aspects of that. But in this particular case, we're going to pass that to a socket as we're creating a socket. We're going to pass it to this resolver. We're going to then connect. We're going to call connect. And then we're going to send some data out. And after that, we're going to read until some condition. And then we're going to, that was the last one was the header. Then we're going to read the body in, which is just reading everything else. So the this I/O context is provided to each of the networking objects, and it contains a variety of different things and policies. And when we get to synchronous, when we get to asynchronous, we'll talk a little bit more about it. Socket. Notice socket's coming from TCP socket. TCP socket meets the Internet Protocol requirements. And there's also a UDP. It is basically a stream socket specialized on TCP. There's one that's also for UDP, which is the basic datagram socket. The resolver is a basic resolver. And the purpose of the resolver is to take a host and a service name and convert that into an endpoint. Or the other way around, to take an endpoint and give you the associated host and service name with it. The resolver is the thing that's going to get us the endpoint, and the endpoint is what we need to connect with. So once we call connect, we're going to pass it the socket that we want to use for the connection, and we're going to use the resolver to resolve the endpoint for us. It's going to associate then, the connect will associate that socket to the endpoint. So in this, where's the error handling? Yeah, it's an exception. Yeah. So for the synchronous calls, we basically have two versions. We've got one that has this error code at the end. The other one is going to throw an exception that's going to match, the type is going to match the type of the system error that would have been generated. So if you don't provide an error code, like this signature, you're going to have an exception thrown. With this signature, you're going to provide the error code. A reference to an error code will be taken, and the error code will be set if there's an error. And you can test afterwards. If there's not an error, you can do something. So if you believe in exceptions are flow control, you actually might be at the wrong conference, but if you do, perhaps reading and using exceptions is the way to go. But most likely what you're going to do is use error codes, and you're going to pass that along so that you can get the error back out and make decisions about what you need to do next. All right? Yes?
The example you showed before, you did the resolving and the connecting in one line. Both of them can throw an error, right?
Yes. So the comment is that both of these operations, the resolving and the connecting, can throw errors. And so I'm guessing the question is what's going to happen? Well, the exception will be propagated up. You're going to get the system error that's appropriate for the exception that was thrown.
You know from where did you get the exception?
The exception will match the type of error that you have. Yep. Different exceptions. All right, so writing, what kind of error handling do we have for this write? Exceptions, because we're not passing in an error code. So on the write, we are passing it the socket, and we're passing it a buffer. I/O is performed through buffers. All I/O is performed through buffers. Buffers do not own the data. The data is not owned by the buffer. I'll probably say this a lot more. When we're debugging problems and helping clients out, one of the biggest things we are fixing is this ownership problem. The wrapper is going to generate a buffer sequence that does not own the underlying data. It simply describes the underlying data. So please do not let your data source go out of scope, all right? Just everybody just shake your heads, yes. I will not do that, Michael. I will not.
Considered renaming it to buffer view?
I've not considered anything, no. All right, so what kind of buffers do we have? There are three types of buffers in the system. There's a mutable buffer, constant buffers, and then dynamic buffers. To create a buffer, you're going to use one of those proxies or factories to get one out. And there are a whole variety of them. So in order to get a mutable buffer, The signature looks like the thing at the top where you call buffer, you pass it something, and out of that you get a mutable buffer. What kinds of things can you pass? Everything from a void star with a size to your container types and whatnot. We have then constant buffers, and as you can see, there are quite a few more of those because string view gets to play inside of the constant land. And then we have something that's a little bit different. If you're not familiar with, if you're familiar with ASIO, the other two will just kind of fall in place. These are a little bit different, and they are dynamic buffers. Dynamic buffers will, as they sound, increase the size of the buffer based upon your needs. And so we can create dynamic buffers from vectors and from strings. And there are two variations for each. You'll see there's one that takes a size t. The size t is the cap, how large you'll let the container grow, and then it needs to stop. All right, so if you're into just letting your networks get flooded and your programs crashed, you want to use the one without that. All right. All right, so here's our write. And so we are iterating through and we're writing by taking and using our buffer to create a buffer sequence and passing that off to the network write. Okay, so there's this thing called synchronous, the delimited read. Read until we're going to give it the socket and we're going to give it a buffer to read into. In this case, we're going to give it a dynamic buffer. Passing in header, so it's going to take this string, it's going to just keep growing it as large as it needs. And then we're going to give it a pattern to find. And it's going to read until the delimiter is contained inside of the buffer. All right, that wording is important. So until that delimiter set is contained inside the buffer. Delimiter is a character or it is a string view. Those are the things that it can be. All right, and the question is, in general, do you check to see if you've made it to the end? Yeah, the question is, how would you know if you've got it if you return? So if you have not received the thing you're looking for, the delimiter sequence, it will block. And so the only way it's going to return is that there's an error. And right now, we didn't pass an error code, so we're going to be throwing in an exception. So how much memory will be consumed with this? Yeah, I don't know, right? We've not capped it. And if we're concerned about that, we should do that. All right, so we've got read here. And we are going to now read from the socket, giving it a dynamic buffer. And we're also going to give it this error code. So how's error being handled in this situation? Well, we've given it the error code, so it will fill in the error code with an error if there is an error. Otherwise, it'll just return. We can test E, and E will return true. All right, we just told it to read, and we gave it a dynamic buffer without a size associated with it. So how long should it read for? Yeah, maybe into file, network, timeout, till, in essence, an error, right? I mean, there's some condition that's going to cause this whole thing to stop, at which point we could probably look at our error code and figure out what that was. All right, so it's going to read, remember this wording here, it's going to read until the delimiter is contained inside of the buffer. It's going to use read sum internally. So if I just read sum, which is going to give me everything that is available right there now inside the system, what's inside the buffer, right? Let's just think about this is maybe DMA down below, and it's DMAing into some buffer, and read sum just goes and grabs whatever is available in the system. It's got some bytes. All right. If you have those bytes and you have your delimiter sequence, what else might you have? Some other stuff. Yeah. You could be really sad if you thought reading with a delimiter just stopped right there, and then the next buffer started right after your delimiter. In fact, that's like one of the other very large errors that we find over and over again. So when we're debugging code, there are a couple things we look for, and this is one of them. Is a read until being used, and if so, it's likely being used incorrectly. So we could replace what's there with instead of a condition, instead of this delimiter match that it's going to make, we can provide to the read a completion condition. So we just say read, give it the socket, where to put the information, and here is something that you can figure out whether we're done reading or not. What this takes is a function that takes the error code and the total amount of bytes read so far in the entire operation, and it's going to return the number of bytes to read again. So can anybody think of like some super inefficient algorithm that we could do this with? If we could search for our, what's that? One at a time. Let's do that because it's super inefficient. So we could just replace our delimiter with a handler, with policy that will tell us whether or not we are done reading. So it's going to search and it's going to check to see whether or not we have an error. If we don't have an error, and some other things, then we're going to return 1, read 1 more. Read 1 more, until we say read 0, at which point the read will be done. Now, we wouldn't want to write this. We want to be a little smarter, but this illustrates this idea of the flexibility that we have on determining how much to read in. All right, let's talk a little bit about some asynchronous things. So at the top, we've been creating this I/O context. The I/O context is an execution context. And the execution context points to an executor. The executor provides the policies and the rules of how to execute items that are going to be in the completion queue. There are lots of papers on executors and a lot of ideas about executors, and we're not going to talk about any of those here. You can read all of those papers. We're going to have a very narrow view of what the executor is, okay? And clicker is not clicking. I'm going to be tethered here. For us, when we have an I/O context, by default, you haven't seen that we've been creating executors or associating executors. By default, we get the system executor. And the system executor represents a set of rules in which function objects are permitted to be executed all at the same time. So if there are multiple threads of execution associated with this thing, and we have multiple function objects that are queued up to be executed, they can just all execute whenever. It also says some other things. Some of them are a little more surprising maybe to you at first, which is that if you throw an exception and the exception is caught within the executor, the system executor will politely call terminate for you. Okay, so there are some things that you may want to find out about your system executor. We're just going to post some work, try to figure out how to use this thing a little bit. So I'm going to create an I/O context. Post lets me just take a callable and post it right on the completion handler queue. And so I'm giving it the context and some lambdas. And I run this, and nothing happens. It doesn't print anything out at all. Nothing's there. What's that? I exited immediately. Okay, I definitely exited immediately. And I didn't actually give it a thread of any sort at all. So the I/O context needs a thread calling run, and that thread that you provide to the I/O context is the thread, or threads in this case, that the completion handlers will be ran upon. Okay, so you're going to provide the threads to the system that you want to be used for running your completion handlers. All right, so I do this again, and actually, it still doesn't print anything out. It just like runs right to the end, and it's done. It's done. Okay, well, I have to call run after there's some work to do. And I call run, and then I give it some work to do. And Gore always asks me, why do you do that? Because if I didn't, then it would just work, and you wouldn't know this. That's one reason. But the other reason is I find that in our systems, we set up our threads first, and then eventually they get some work to do later. And that's just the common way that we set things up for the way that we're doing work. So we need to somehow tell the executor that it has work. There's something to do. It appears like your queues are empty. You have nothing to do. You might as well just return. But the reality is, I don't want you to do that. And the way we do that with the networking TS is we use a work guard. So we can use make work guard. We provide it the context. This is the I/O context. And then the object that comes back, either the lifetime of that object, or, as you can see, we call reset when we're done with it. That will say that it's not interested anymore, or on the destructor, it will call reset. That will remove the work object out from keeping the queues alive. So we need to give it this work queue. Now everything works great. So we've kind of see what the setup here is. We've got threads that are going to be calling run. Those are the threads that are going to be utilized. And we probably want to get a work guard in there before work occurs so that the threads do not just return immediately. So everything inside the asynchronous system starts off with this initiating function. We just saw post. Post is, in essence, an initiating function, but it's not going to actually do much work. The initiating function puts us inside of this operation outstanding state. Things will sit in there until resources are available to do whatever needs to be done. All right? So as soon as the resource is available, like maybe we're doing a network read or a network write, as soon as the resource is available, then that operation can be performed, and we will be able to see the side effects. Once the thing is completed, then the completion handler is submitted to the executor. That completion handler will sit inside of the operations completed state until until the completion handler is called. And the completion handler will be called based upon the type of executor that you might have and the policies that are associated with that. We just learned the system one, the policy associated with, it's happy to run everything all at one time. So however many threads are available, and if there's something inside the queue, it'll go ahead if there's a thread available and run it. Things that are async underscore, start with async underscore, those are initiator functions.
Spelling error.
Thank you. Yeah, sure is. Yeah. Yeah, that stinks. All right. What if we didn't want that? So the last couple slides, we've been doing I/O output to the console, and we're doing it all at the same time on multiple threads. We'll probably have like mishmash whatever, right? We've got a mess. How many of you have written from multiple threads to the same TCP socket at the same time before? We'll just say by mistake. Didn't know about it. Or on purpose, because you thought it'd be cool. Still fewer hands. Okay, it's a mess. Don't do that, all right? It just makes a mess. So if you have a situation where you want to control differently, you can provide a different executor to do that. And Strand is one of those. Strand's policy is one in which only one item will run at a time that's associated with the strand. So we've added the strand, and now what we do is instead of passing, before we were passing the context to post, we are going to pass the strand to post. Strand is an executor. It's going to now have the policy of how this will be ran. And even though we have two threads, both of the items that we've posted are associated with the same strand. So only one will be ran at a time. Okay, unlike, if you're familiar with ASIO, unlike ASIO, there's another guarantee that's in the networking TS, which is that ordering is maintained. So the order in which they arrive at the strand, posted to the strand, or given to the strand, is the order that they will run. All right, so far, this last item has been this completion token. We've seen callables there. But they can actually be a little fancier. We can put other things in there. For example, we could put in use future. And now what happens is this says return a future, please. And the future now can be used in order to determine when the operation is complete. What is the type of the future? Well, it's not going to be the error. It's going to be whatever other than the error would normally be passed to the completion handler. So completion handlers receive an error and something else, something useful. It's the useful part. The error will still be received as an exception that's thrown when you do the get. All right, so I am not going to go in great detail on this because we're going to run out of time. And it is a mess. And I'll explain later why I think actually trying to do a lot of asynchronous things using futures is a mess. So you want to probably know, does this work with Gore routines? You probably tried to say Go routines, but this is Gore routines. Gore routines and stateful coroutines. Does this work with the same thing? Well, actually, yeah, it does. This one actually is the Gore routine version because Gore wrote it. So we can see that we can use async send, async read until, async read until again with co-await. And now it looks a lot like what our synchronous code looked like, but it's happening asynchronously. Now, so how does this work? Well, these are not the networking TS versions of these calls. Gore also wrote some wrappers to help along with that. And so these wrappers are reusable, so I can just continue to reuse these wrappers with async connect or send or read until. And if you want to find out a whole lot more about this, Gore will be speaking about naked coroutines live with networking tomorrow at this time. All right. So another way that we could do this is we could use completion handlers and callbacks. So we're going to set this up very quickly. We've got the same types of things that we've been setting up before, that same boilerplate. And we're going to have this home page getter. We're going to pass it the IO context. We're going to do get page, passing it what we want to get the page from. And it returned a future. We can then get on that future the result back out. So what does it look like underneath? In this case, this is a class, and this class has a few things. Has this get page, but privately it has a connect method, read header, read body, and send request. It has a few other things, a reference to the IO context. It's going to contain the socket, the header, the body, and then the promise that was being fulfilled later. So remember, we have this initiating function that's going to get everything going. And after the asynchronous activity completes, the completion handler is going to sit on the operation, is going to be in this operation completed state, and then it's going to get called. And when that gets called, the normal thing to do using this model is then to initiate the next asynchronous item that you want to do. So during the completion of the previous asynchronous activity, start off the next asynchronous activity. I finished reading the header, and now I want to start reading the body. When do I start reading the body? Well, in the completion handler of reading the header. So we're going to be able to chain these things together. Get page just sets some things up, calls connect, returns the future out of the promise. And what's connect going to do? Connect is going to use a resolver called call async connect, and then pass a lambda that is going to take the error code and the endpoint. It's going to check the error code, and if there isn't an error, it's going to send a request passing the host, and then start the read of the header. Otherwise, it's going to set the exception for what the error was that it received on the promise. The completion, the lambda is the completion handler. The lambda will get ran after the side effect has occurred. So what does send request look like? So send request, we've got the request. We're going to call async send. I don't really care about the completion handler because I don't care what it does. Pause another second. What's that? Bam, good job. There's a bug. All right, what is the bug? Okay, what if it doesn't send anything? What else is a problem? Yeah, the buffer is a big problem, isn't it? Yep, so here I am passing this request, which is a temporary string, to buffer. And so I'm going to get a buffer sequence of a temp. I'm going to be pointing some temporary something or another, which is going to go out of scope, probably in the middle of the send. And life is going to be bad, right? It's going to work maybe occasionally. It's probably going to work at my desk, but it will not work like occasionally for QA, but you know how that works. So yeah, this is that typical bug, right? People get very excited about this. They pass it off to buffer and bam. So the read until, for the header, we're gonna start that off, giving it the same tokens that we were looking for before, the same delimiter. And if we don't have an error, we're going to go ahead and read the body. If we do have an error, we're just going to end there and return the exception. All right, so this is that chaining thing again, right? And if we look at read body, what does it do? It is satisfying the promise. One way or the other, it's going to satisfy the promise. So either it's done and it got the answer, or it's not. Now, what does chaining look like? What is that? Is that familiar to you? About anything else? It's callback hell. Okay, that's what it looked like to him. Yeah, anything else? Yeah?
Beautiful state machine.
Thank you very much, Gore. It looks like beautiful state machines. I wish I could say it like Gore says it. Beautiful state machines, yes. Okay, let's talk about a couple more things. Let's talk about a chat server real fast. We're going to have this client that's going to connect into some generic server. It's got the word ASIO in there. That's because it works for either. And the generic server is going to hand off the client to the chat handler. And another client's going to connect in, and it's going to now hand that off to another handler. The handlers are representing the state on the server side with talking to this particular client. All right, they're going to maintain the connections. So the steps are, it comes in, it connects to this listening. The listening gets handed off to the client handler and continues to do the communication. Who owns the client handler? Who owns this thing?
I'm guessing it would own itself.
You are right. Pablo suggests that this should own itself. It should own itself. That's right. Yeah, so in a lot of places that we see code, there is a manager of some sort that owns it. And the manager occasionally has like some cleanup call that goes through, and it checks to see what isn't active anymore, and it reaps those. Out of college, my very first manager out of college, we're sending a design review, and he got very upset and says, managers are not supposed to do anything. And I was thinking, oh yeah, that's right. Managers are not supposed to be doing anything at all. So don't make manager classes. The client handler should own itself. So now we need a mechanism to make sure that the client handler owns itself. What keeps that client handler alive? Well, it stays alive as long as it has work to do, right? As long as it has something to do, something to read or something to write, it might as well hang out still. So thinking about our chaining of completion handlers, we are going to queue this async read, which is our initiating. And on completion, we're going to call read done. And what does read done do? Well, if there weren't any errors, it's going to start off the async read again. And if there were errors, it's going to not do anything anymore. It's just going to fall out. The canonical way to set this up is to inherit from shared from this, enable shared from this. And what that's going to allow us to do is to take a reference, a counted reference to ourself, and bind that up into the completion handler that we give off. So when we give these things off and they're hanging out inside of the executor, or they're waiting to be given to the executor, that object's lifetime will be maintained. So async read until, and now when I form the lambda, I'm going to take shared from this, set that equal to me. So now it's bound up in there, it's captured, and that will extend my life. The lifetime of this object will continue as long as this asynchronous operation is queued up. And when that operation completes and the completion handler is given to the executor, it still has a reference. And when the completion handler is called, it still has a reference. And when that completion handler is called, then it should probably queue up another task, or it should do nothing, right? It's done. It's reached the end of what it needs to do. And that separates the read from the write. Reads can make decisions on their own, and writes can make decisions on their own. And when there's nothing else to do, then the whole thing can come back down again. It can destroy itself.
It doesn't know. That means it doesn't know itself. It stores itself in the objects it can solve, which means it's getting all through some magic by the executor.
It controls the ownership of itself.
Yes, but it doesn't actually.
We'll get philosophical here. I'll be Tony. Do any of you own yourself? All right, let's actually just kind of move on here. Actually, we can do this. So it's this thing that we want to look at again. The initiating functions, when we're inside of our completion handler, when it's being called, that's when we want to start the next initiating function. And the completion handler for that, we want to actually bound up into that a reference to the shared from this in order to extend the lifetime. Okay, when we're assembling these things and putting them together, we want to start decoupling our services. So we want to decouple the fact that we are processing the communication from, that we're receiving the communication from the processing of the communication. And so there are a variety of different ways to do these layered designs and the way to decouple them. We can use the executor as a processing executor. We can give it work to do. We can start combining things with Boost, MSM, or SML, or Spirit. The first two are state machine libraries because, at the end of the day, what we're trying to do is actually create a state machine. What I'm trying to do is create a state machine. I'm trying to convince you that you want to do the same. So you want to choose your abstractions based upon the complexity of what you're solving. Sometimes, actually, the stream abstraction that I had at the beginning is what I need to solve the problem that's at hand. I don't need anything else. That'll do exactly what I need. I shouldn't make things more complicated. Sometimes that's the right answer. Sometimes synchronized communication is the right answer. So I just do that. Sometimes it needs to be asynchronous. But when it's asynchronous, I need to choose what fits there too, because there are a whole variety of different ways to solve this. So this is my problem. Most of the communication problems I see that people throw up are simple, very easy to solve, and chaining futures is easy to do. This is a very easy communication protocol that had to be implemented. It's actually, if you saw Talk is Talk last night, this is MQTT. This is what it needs to go through. It runs on little itty-bitty embedded thingies. So here's the hierarchical state machine for it, and the one on the right-hand side we haven't blown up. This is the blow-up of that. Communication protocols are much more complicated than sometimes we think they are, and you start falling into a trap when you chain things together that you're not sure how to get out. But that's not actually the real problem. So let's see what the real problem is. By the way, this is that state machine on the right-hand side. If we use a state machine library to write this, we can just write tables. And the tables are super easy to understand. Not only that, we can figure out whether they're correct or not because we know what's missing when we look at it. We can actually verify that we handle all the states with all the possible events coming in that are required. And when an event comes in that we don't know what to do about, we know how to handle that because we're going to use a hierarchical state machine type implementation, so we can handle our errors at layers that are appropriate for the errors. So don't try to destroy the state machine that already exists. Just give in. And use the state machine library. So let's think about futures for a moment. So what is the concept of a future? A future is a synchronization thing, right? It's an object that helps me synchronize. And on the left-hand side, at the top, we can think about at the top is the part that's initiating the asynchronous activity. It's going to start something else happening. And on the right-hand side, as it runs on through, there's a shared state. And we call the right-hand side, the shared state of the right-hand side, the promise. But that's the asynchronous provider. And the left-hand side, somewhere else, something wants the result out of that shared state. It wants the result from that asynchronous operation. And we call that the future. But the way the futures work is that at some point, we need to get the answer back out. And to me, this is why it breaks down. I need the answer back out somewhere. Where in the last few examples had we needed the answer back out? We don't need the answer back out because it's an event-driven system. I don't have a place where I'm going to call get. If I have a place where I'm going to call get, it's on some thread that's sitting somewhere, going to call get. So for us, most of our networking and our asynchronous communications that we deal with, they want to be event-driven. So the question is, how about coroutines? Does it fall apart with coroutines? Because when I look at this, it looks like it's starting to fall apart. I've got this read until, and it looks like I've just kind of taken this whole concept of asynchronous, event-driven stuff over here and brought it on in and just made it serialized with some sugar. So will this do that? You know, I have this FSM process the event. I'm passing in the parsed message into there. Well, what we haven't seen yet is how is the coroutine running? What is running the coroutine? And in essence, the coroutine is running on the same run thread. So with the future, I'm trying to synchronize things from the run thread, from the I/O context, from the asynchronous activity that's going on, into something else. And so that's the synchronization point. With the coroutine, it's all running still inside of that run thread. And as a result, it looks serialized. It looks like this nice procedural code, but it's still kind of, in essence, still doing my event handling for me. So I can have this small little event loop in which I'm processing events, and I'm passing them off to the state machine that's going to actually figure out what to do with it. And if you still love completion handlers, you can still do that. In which, at the end of reading, you go ahead and pass off the event to the state machine. So this also handles, of course, obviously, handles the event-based type processing. So we've got two mechanisms that will handle that very smoothly, and then we've got one that doesn't necessarily fit real well. But it fits really well when we need other types of processing. So if you need event-based processing, don't try to use futures and promises. Do something else. And if you can use futures and promises, those are a lot easier to use for synchronization devices. Use that. If you can use the synchronous, use that. And if you can use streams, everything fits on one slide. And you're like a hero. And you can make fun of the Rust people. All right, some takeaways. The networking TS implementation exists. Go use it. It exists out of the base of Asio, which has been around forever. And so go grab it, play with it, see how it works for you. It has a flexible mode for handling execution, supports events, coroutines, futures, other mechanisms. That completion token that gets passed can be customized for all kinds of very interesting ways to handle your completion routines. If you know ASIO, you almost know the networking TS. All right. It's time for a few questions, it looks like.
What's a mode?
I don't know. What is a what? Another typing error? You making fun of my typing errors again?
Yeah.
Yeah, stop making fun of my typing errors.
Just want to make sure it wasn't a concept I wasn't aware of.
I thought heckling was going to be coming from over there. Any other questions other than spelling errors? Pablo.
In one of the slides, I think you may have gone back too fast. It was a while back, so don't bother trying to find it. You had the issue where the buffer was a local variable and it was going to go out of scope. I don't remember if that example also had a lambda. Do you want to talk a little bit about the scope of the lambda? Lambda is also a local variable, isn't it?
Okay, yeah, it also had a lambda. The lambda is going to be moved into it.
Oh, I see. Okay, it's going to be moved.
Yeah.
Okay.
Taka?
You mentioned don't create a manager class in chat example. Okay.
In the chat example?
Yeah, chat handles, owns themselves. Yeah, but your example is chat means a typical chat. Finally, the receiving message should be delivered other chat handlers. So finally, we need something management class. What do you think?
Yeah. So the question basically is what do you do when you have to have management, right?
Yeah.
So what we do is, in this generic thing, where we've got a generic listener that's handing things off to the chat handlers, the generic listener has a callback handler into the system somewhere. So the system generates one of these. It passes in as a template parameter what the client handlers look like, and it calls like set connection handler. And every time a connection comes in, it actually gets passed a shared pointer to the connection handler, to the client handler, and it could store off weak pointers.
Oh.
And that's how we handle the problem. When we need to still have management back into the handlers, we keep a weak pointer to it.
Okay, thank you.
In one of the slides, you had a send request that returns right away, and you didn't care about the completion handler and then a read header. That made me itch a little bit because usually I would do a send request, and in that completion handler, then I would start reading the header.
Yep.
Talk a little bit about why is it okay to do it the way you showed it?
Okay, the reason I did it this way was just because it's trying to mimic what the previous examples did, where it's sending out the HTTP request, and now it's waiting for the responses. So the request, I don't really care when it goes out and when it finishes, because the responses back are going to come back on the read header and the read body. Normally, you would set this up so that the completion handler would start off the next read, or it would look to see if there's some new message that it has to take care of. I'm sorry, the next write, or check to see if there's a new message. That's what the normal
Yeah, I
pattern
don't
would be.
think it would be an error, but you can't really handle errors, for example, when you send a request. Like,
No,
yeah.
no, you're right. I'm not handling errors at all. That's correct.
Yeah, hi. Do you still need to feed a bunch of threads to the context if you are going to use futures and coroutines?
Do you need a bunch of...
To pass a bunch of threads to the context.
Okay, so the I/O context needs to have at least one run called on it, because the run methods that are called are the threads that are going to handle the completion queue. So there has to be at least one, and one is probably fine. Now, do you have to have them for coroutines? Was that the other question?
Yes.
Yeah, because the coroutine is, that's actually the thread that the coroutine is working on. So even though we've got this magic here, in the top one where we have co-awaits, and there's some other part, right? These two parts pinging back and forth, that's all running through the run thread.
But in this case, only one thread will run the continuations.
That's correct. Only one thread is running the continuations.
Okay, thank you.
Oh, and my session's over just in time. No, sorry, David, go ahead. This is the question I don't want, I'm sure.
I don't think you mind. This read until thing, it can add extra stuff to your buffer.
Yeah.
And then the alternative you showed was reading 1 byte at a time.
Yep.
And that has its own problems. So what is the solution?
Okay. Yeah. So if read until is unsatisfying and reading 1 byte at a time is unsatisfying, what should you do? Great question. So we use read sum and for everything and build on top of that because that reads whatever is available that the OS has already read in, and we just get that and start reassembling the packets the way we need to. So it returns immediately, or it blocks if there's no data. And if there's no data, it blocks until the first full buffer, usually it's a packet size from TCP, is ready.
So you just have to do a bunch of extra work to...
Yeah, we've got to build our protocols on top. And we've found that that's the fastest way to build, or the fastest running protocol. That's it.
Thanks.
Thank you.